Okay, so last week we have learned the whole carbon footprint, right? Which is carbon emission value for each year, and it has already account for the embodied carbon, the operation carbon, and also the transport carbon. Okay, so today we will look into some emission reduction strategies. And it will be mainly focusing on the reduction of embodied carbon, operation carbon, and to investigate the possibility of reducing the operating carbon by renewable energy. Okay, so that's the lecture content for today. Okay, reducing embodied carbon. So embodied carbon would be the carbon emissions due to the construction material, okay, extracting the materials and then transporting the material to the factory and manufacturing and then transportation. So all these emissions, including the landfill, okay, when we throw it away, okay, whether you throw it to the landfill or recycle or capture the methane emitted from the landfill. So the whole life cycle concept, okay, for the calculations of embodied carbon. So this is related to the construction material, okay. So when considering the opportunities to reduce the embodied carbon of a project, it is important to note that the greatest potential to reduce carbon is at the conceptual and planning stages. So before the detailed construction stage, or before the detailed design stage. So at the very early design stage, so about the concept, about the preliminary design, the building orientation, and then the facade material. So all these will affect a lot, okay, the potentials of reducing the embodied carbon. So the approaches, okay, maybe build nothing, okay, so instead of new construction, maybe we can reuse the existing structure, reuse the demolition material, and build less, okay, repurpose, refurbish, extend an existing building, revitalization, and build clever, okay, design optimization, construction methodology, material selection. So choose the low carbon material, or maybe choose the material with higher recycled content, and then maybe the construction methodology will allow you to extract the material for reuse at the end of the building life. Okay, build efficiently, use low carbon construction technologies, minimize the wastage, simple design so as to reduce the material wastage. So all these are approaches to reduce the embodied carbon. And this is a figure. So on the y-axis, this is the carbon reduction potential. So in the planning stage, so early in the design stage, the potential is very high, okay, because nothing is confirmed, okay. And if you can build nothing, okay, so based on the existing building, so we just reuse the existing building, then the potential for carbon reduction will be very high. And then next we'll build less, okay, maximize the use of existing building, okay, reuse the existing building, and then maybe just some revitalization, renovation. And then the potential will be a bit lower, okay, and then build clever, okay, optimize the material usage using low carbon material, and then build efficiently, use low carbon construction technology, eliminate waste, and decarbonization, deconstruction, and so this will be related to the possibility or the potential of carbon reduction. So to minimize the embodied energy, we may have these approaches. So use low carbon materials. For example, bamboo. Okay, so bamboo can grow very quickly, very fast. Like some kind of bamboo can grow over 10 cm in one night. Okay, so using bamboo for the flooring or for the partition could be a good way to reduce the embodied carbon. And and some renewable material like the cork or some linoleum, okay, they are also low carbon material. And we may import materials from nearby regions. So why nearby regions? Because if we import the materials from far away, then the transportation carbon could be very significant. Okay, so we may use the local material as much as possible so as to reduce the transport carbon. Okay, recycle. We may recycle the material if we demolish a building, or we may use material with higher recycled content. Okay, maybe recycled steel, recycled concrete, or maybe some material that are made from recyclable materials like aluminum and glass. Okay, and we may use glass block. Okay, some building block which is made from waste glass, eco block made from waste glass, and reuse. Okay, so reuse the existing material. So reuse the materials and products or the elements from the existing building. And or there is an approach called deconstruction. So deconstruction is that when you tear down the building, so you will carefully and partially dismantle the existing building so that you can recover the building materials, okay, and these materials can be reused elsewhere, okay, in other new building. And reduce, okay, so how to reduce the building material? So if we don't change the design, then it could be quite difficult, okay, so the building design will determine the possibility of reducing the material use. So maybe we can improve the buildability, use some simple design, modular design. So for modular design, it will be more probable to reduce the material wastage. And lastly, adopt prefabrication. So like MIC or the MIMEP, so using modular prefabrication, so instead of on-site construction, okay, we may move the manufacturing or the building process inside the factory within a controlled environment, then the material wastage can also be reduced. Embodied carbon must be considered over the lifetime of a building and not just the initial construction. So during the operation phase of the building, we may need to refurbish the building, renovation, or some fit-out project from time to time. So for a new 21-story steel frame office building with 3 basements level, the embodied carbon breakdown could be like this. So for the substructure, superstructure, facade roofing, the building surfaces, the fit out, we may have initial construction and some replacement. So this is the initial embodied carbon. And there will also be some recurring embodied carbon. Okay, maybe you have to replace some of the facade material, the roofing, and then replace some of the building surfaces equipment. And the fit out, okay, the fit out embodied carbon could be quite significant because like maybe every 5 years, every 10 years, we may need some fit out for the interior, okay? The key materials that typically account for over 70% of the embodied carbon in the life cycle of the office buildings may include these. Okay, so these materials typically will constitute like at least 70% of the embodied carbon. Okay, so we have concrete, steel, timber, masonry, window, curtain walling, carpet, plasterboard, and furniture. Okay, so these total will add up to around 70% of the building embodied carbon. So we will look into these material one by one. And please note that for this material, okay, we will be focusing on the embodied carbon. But embodied carbon is only an indicator to global warming, okay, to greenhouse effect. But other than the greenhouse effect, other than the climate change, there are other impacts by this material. Maybe toxic material, maybe the consumption of water, or maybe air pollution, or maybe ozone depletion and others. Okay, but for this subject, the impact would be global warming. Okay, would be the greenhouse gas emissions. Okay, the first kind of building materials that we will discuss is the concrete. So concrete is the world's most commonly used construction materials and is probably used in some form in every new office building. Okay, no matter it is a concrete building or a steel frame building or a timber frame building. Okay, more or less we will use concrete. Okay, so for concrete building, yeah, of course the structure will be concrete, okay, maybe reinforced concrete. And for a steel frame buildings, okay, even for a steel frame building, okay, the whole structure would be in steel, okay, but there may also be concrete floor slab, concrete core walls, and so on. And for timber frame building, we may have a concrete foundation. Okay, so for nearly any kind of new building, we will more or less use concrete. And what is concrete? So concrete is a composite material. Okay, it consists of different kind of materials, and it includes some fine and coarse aggregate. Okay, which are crushed stone, bricks, rocks, sand, water, and mixed with cement. Okay, so this is the concrete, and concrete will need some time to cure. Okay, so it means it needs some time to be hardened. Okay, so it will be hardened after some times. And concrete is one of the most durable building materials. It provides superior fire resistance and also thermal insulation, and it gains strength over time. Okay, structures made of concrete can have a long service life. Okay, 50 years, 60 years, no problem. Energy requirements for transportation of concrete are low because it is produced locally from local resources. So for those crushed stones, rocks, sand, so they are usually available locally, right? Nothing special, just some rocks and stone and sand and water. Okay, so these are available locally, so we don't need to import these materials far away. So the transportation requirements, the energy or the carbon emissions will be usually low. But okay, the major carbon emissions due to the use of concrete come from cement. Okay, the main ingredients, okay, include cement, okay, and also the sand, water, and mixture. So these are not problem. Okay, for the cement is the major contribution of the carbon dioxide. Okay, little energy is used in producing and combining the raw materials, but large amount of carbon dioxide are produced by the chemical reactions in the cement manufacture. Okay, when we manufacture the cement in the factory, it will emit a lot of carbon dioxide. Okay, the most commonly used cement is called the Portland cement, which accounts for around 95% of the embodied carbon of a typical grade structural concrete. Okay, so 95% of the carbon emissions in concrete is due to the use of cement. So how carbon dioxide is being emitted? The raw materials of cement is the limestone. Okay, limestone is the major ingredient of cement, of the Portland cement. And this limestone, which is calcium carbonate, will be burned to remove the carbon. So in this chemical process, carbon dioxide will be produced. Okay, so we put the calcium carbonate in a kiln, okay, in a large oven, okay, to heat it up, and then chemical process will occur and carbon dioxide will be emitted. And besides, when we heat up this limestone, okay, for this chemical process, we need to input heat, okay. So in order to produce this heat, we need to burn some fuel. Maybe we burn the fossil fuel. So if we burn the fossil fuel, then carbon dioxide will also be emitted. And this cement will be manufactured in a factory, okay, not locally in the construction site. Okay, so they will be manufactured in the factory. So when we need a truck to transport the cement to the construction site, and the truck may be using some gasoline or other kind of fossil fuel. So once again, carbon dioxide will be emitted due to the consumption of these fossil fuel for distributing the cement. Okay, so the use of cement will result in carbon dioxide emissions in 3 ways. Okay, first of all is the chemical process, okay, for the production of the cement. Second is the use of fossil fuel for inputting heat to the chemical process. And then thirdly is due to the transportation. All right. Okay, so can we replace the Portland cement with some other materials? Yes, we can. Okay, a proportion of Portland cement can be replaced in the concrete mix with some waste byproducts from other industry, and it will reduce the embodied carbon and also the cost. Okay, for example, by the use of the pulverized fly ash. In short term, we call it the PFA. Okay, it is a kind of fine powder, and it is a byproduct by burning coal in the power plants. Okay, so for some power plants, for generating electricity, they may burn coal, right? The fossil fuel coal. And the byproduct is this kind of fly ash. And we may use the fly ash, this kind of fly ash, and mix with some Portland cement in order to reduce the carbon emissions. And we may also use the GGBS, which is the ground granulate blast furnace slag. It is also a waste byproduct from the production of iron. Okay, so for the production of iron, this kind of slag, this kind of also fine powder will be produced as a kind of waste. So we may once again mix with the Portland cement and then reduce the carbon emissions. Okay, but you have to understand that by mixing these products instead of using the Portland cement, we may change like the color of the concrete and also the curing time of the concrete. So typically we need like 7 days, okay, like a week for the concrete to cure. Okay, but by using these replacement, the curing time could be longer. Okay. Apart from the concrete itself, we also need a formwork. Okay, a mold to shape to shape and support the liquid concrete. So the formwork used to pour concrete accounts for up to 5% of the embodied carbon in a concrete structure. So maximizing the use of the times, the number of times that the formwork is used, and then avoiding sending it to the landfill are two main methods of reducing the embodied carbon due to the formwork. Okay, so in Hong Kong, we may use the timber formwork. Okay, we use some wooden panel as the formwork to form a mold and then pour the liquid concrete and wait for 7 days for the concrete to cure. And we may also use steel formwork. Okay, so as much as possible, we should reuse these formwork. Okay, so as to reduce the waste and therefore the carbon emissions. These are just some numbers for your reference. Okay, these are the typical embodied carbon for different kind of concrete. But you need to understand that the uncertainty could be high, okay? Because we don't have a very standardized method for the measurement or for the estimation of the embodied carbon. Okay, so these are only for your reference. And the next kind of material is steel. Okay, steel is extensively used throughout the construction industry. So maybe for structural steel, for the structural frames of the building, for the columns, for the beams, and to provide the necessary strength and the load-bearing capabilities of the building. And steel will also be used for the reinforcing bar. Okay, we call it a rebar embedded in concrete. Okay, so only concrete is a material that is strong for compression. Okay, so for concrete is strong when it is compressed. Okay, but it is very weak in tension. So in order to strengthen the tensile strength of the concrete, we may add some rebar in the concrete. Okay, so that's the commonly used of steel in the construction industry. And also steel framing, okay, like the use of steel in the walls, in the floors and ceiling, and also steel cladding and roofing. So for the steel cladding, it is usually more durable and then resistant to the weather, and it looks good. Okay, so steel are also commonly used for the cladding. And steel piping and fixture, okay, like the steel conduit and maybe some trunking, air duct. Okay, primary steel is produced by reducing the iron ores to iron in a blast furnace and then converting to steel in a basic oxygen furnace. The main inputs are iron, coal, limestone, and recycled steel. Okay, so this is called the primary steel. Okay, not much recycled content. And for secondary steel, it is produced in an electric arc furnace from recycled steel. Okay, so primary steel, basically from virgin resources. And then for the secondary steel would be from recycled steel. And this figure explains the production of the primary steel and the secondary steel. So for the primary steel, we have the iron ore, limestone, and the coal, and then they are processed and melt and put it into a mold and roll into some steel bar. And for secondary steel, okay, we have the recycled steel, these metal, and then put it in the electric furnace, and then also melt and roll into this steel bar. Okay, so just for your information about the primary and the secondary steel production process. There is considerable disagreement about which embodied carbon factors to use for steel. Here this ECO2. So E means embody. Okay, don't mix it up with carbon dioxide equivalent. Okay, remember we have a unit called carbon dioxide equivalent, and it is a unit for adding up the carbon or the global warming effect due to carbon dioxide and other kind of greenhouse gases by incorporating the global warming potential. Okay, so that unit is carbon dioxide equivalent. Okay, but here this E, CO2, means the embodied carbon. So this E stands for embody. Okay, so there is considerable disagreement about which embodied carbon factors to use for the steel. Much of this stems from the choice of boundary conditions. So whether the benefits of recycled content in the steel when installed or the benefits of the recyclability of the steel at the end of its life in the building should be incorporated. Okay, so steel is a kind of expensive metal, and therefore, whenever it is possible, the steel will be recycled. So it means that when we calculate the embodied carbon, it is already a norm to recycle the steel. Okay, so yeah, it may generate some disagreement for measuring the embodied carbon. Okay, whether to include the end of life embodied carbon or whether it is throw it away to the landfill or recycle. So there could be some disagreement. This video shows the process of recycling steel. So if you have time, you can take a look. So based on some data, worldwide around 83% of the steel is recovered from the waste, because steel is very expensive, very valuable, and therefore we don't want to throw it away. And instead of recycling the steel, okay, means we collect these waste steel and then melt it and roll it to new steel. So instead of recycling, actually we should reuse the steel as much as possible. Okay, so recycle and reuse the steel, they are different. Okay, recycle means that we put them into an oven, okay, melt it and then roll it into some secondary steel. Okay, this is recycle. But here we are talking about reusing. So instead of melting the metal, we just reuse it. Okay. So reuse of the construction products involves their reuse with little or no reprocessing. So reuse offers even greater environmental advantage than recycling, okay, because there are no or very few environmental impacts associated with the reprocessing. Reusing steel from a demolished building will save the embodied carbon provided it is used efficiently in the new building. So the BRE, which is the Building Research Establishment, estimates that around 96% of the environmental impact reduction compared to using new steel section. Okay, so by reusing the steel, we can save 96% of the environmental impact. So in order to allow the steel to be reused, we may use bolt and nut connection. Okay, so instead of weld the steel together, we may use bolt and nut so that they can be dismantled easier in the end of the building life. And it is also encouraged to mark the strength, the grade of strength of the steel on the steel itself. Okay, so have the steel member permanently marked with their strength grade. So it will also allow easier reuse of the steel. Okay, the next material is timber. So timber is a naturally occurring and renewable material that has been used in buildings for many years, okay, like hundreds of years. If sourced from the certified sustainably managed forests, then it is almost carbon neutral, with only some carbon dioxide emissions due to the forestry activities, processing, and transportation. So sometimes we call timber is a negative carbon dioxide emissions product, okay, because when it is alive, okay, when it is still a tree, it will absorb the carbon dioxide. So some manufacturers claim that timber delivers carbon negative structures because the trees and it will absorb the carbon dioxide from the atmosphere and store the carbon in their biomass. And replacing trees by some other trees can also continue to absorb the carbon dioxide from the atmosphere. So sometimes the manufacturer will claim the timber to be carbon negative. So carbon negative means instead of emitting carbon dioxide, it will absorb the carbon dioxide. So contribute to negative emissions. So that's why we call it carbon negative. However, what happens at the end of life of the timber element cannot be ignored. Okay, so it is, yes, carbon negative until it is thrown away. So how will you treat it when it is the end of its lifetime? It matters a lot. So whether it is reused, okay, reused elsewhere, maybe the timber element will be reused in another new building, okay, or recycle, okay, crush it and then maybe use it for some particle board, and maybe use the biomass for generating electricity, or sent to the landfill and wait for it to decompose. And when timber decomposes, it will emit carbon dioxide and methane. Okay, so it means that the carbon dioxide stored inside the timber earlier will be released to the atmosphere when it decomposes. So how you treat it when it is the end of its time will matters a lot. So yeah, when these wood products decompose and then undergo some anaerobic decomposition, then carbon dioxide and methane will be released. And they are all greenhouse gases. And of course, you may also capture these methane maybe for power generation. Okay, so how you treat the waste will affect the embodied carbon. So for example, if sustainably managed forest is used to produce the timber and at the end of its life, it goes to a landfill with no methane capture for biogas, then the emissions will be like this. So let's take a look at this figure. Okay, we have a ton of wood which is manufactured from a sustainably harvested forest, okay? And in order to produce this 1 ton of wood or timber, the trees will absorb 1,516 kg of carbon dioxide. Okay, so you see it is negative, okay, because it will absorb this amount of carbon dioxide. And then the timber, okay, the wood will go through some manufacturing process, okay, maybe cut off and then some processing. And these process may also consume some of the fossil fuel and result in carbon dioxide emissions. So let's say during these manufacturing process, okay, 425 kg of carbon dioxide will be released. And these timber will be transported to some distribution point. And in the transportation process, certain amount, like 39 kg of carbon dioxide produced. Okay, and for the timber, okay, it will be used for constructing a building. And maybe after like 30 years, okay, when this building has to be demolished, you have several ways to treat the timber. Maybe you burn it, Okay, when you burn it, it releases certain amount of carbon dioxide. Maybe you reuse it, okay, reuse it in another building. Or maybe you send it to the landfill, but capture the methane for some other usage. Okay, maybe capture the methane and then use it in a power plant. Okay, so if we allowed it to decompose in the landfill, okay, we may cause this amount of carbon dioxide emissions. Okay, just sit it in the landfill. So the total carbon emissions would be, okay, the absorption of the carbon dioxide, okay, plus the carbon dioxide emissions during the manufacturing process, and during the transportation process, and during the decomposition process. So this would be the total. All right, and you can see that there are a lot of assumptions. Okay, we actually are not certain how these waste will be treated. So whether there will be some biomass for burning and then produce energy, or reuse, or throw it to the landfill, we don't know. So timber is incorporated into a range of engineered products, such as, so apart from solid wood, okay, solid timber, okay, timber may also be used in the plywood, glulam beams, cross-laminated panels, or we call it cross-laminated timber, CLT. Okay, very structurally sound timber can be used for beams and columns. Okay, composite wood products such as particle board or MDF. Their manufacture uses energy and various kind of chemicals like resins and glues. So in order to produce the plywood or this CLT, we may need to use a lot of resin and glue. And all these are chemicals. So these process can complicate the recycling or incineration at the end of its lifetime. Okay, because of these chemicals, recycling these kind of engineered product may be a little bit difficult. So wood waste containing chemicals is typically either used as biomass, just burn it, okay, or just sent to the landfill. So once again, these are some reference embodied carbon for your information. And once again, there are many uncertainty of these products. Okay, one factor is that there are water in the timber. Okay, so the moisture content will affect its weight. And these embodied carbon value are per unit weight, okay, per kg, per unit weight. So the moisture content will change when you process the timber, right? So after some time, less and less moisture. So how you define the weight of the timber, okay, could be a question, okay? And besides, the fossil fuel, the type of fossil fuel you use for the processing of the material, whether you use coal or natural gas, okay, or renewable energy, okay, will affect the carbon dioxide emissions. Okay, so these are just for your reference. Reused timber has about 75% lower environmental impact compared to new timber, just like steel, right? Reusing the steel can save like 90-something% of the impact. And reusing timber has 75% saving. So new timber can provide lower embodied carbon solution in office building, provided that it is sourced sustainably. Okay, from some sustainably maintained forests designed to maximize design life. So we have to design the timber such that it can be used for many, many years. Okay, otherwise the embodied carbon will still be large. And manufacture with non-toxic chemicals, without those like the resin or some kind of chemicals coating, okay, and it will simplify the recycling after its end, the end of the life. And don't send it to the landfill, okay, then it will make more justified for using new timber. And the next kind of material is masonry. Masonry will be building wall using bricks, stone, concrete block, glass block, and then bond them together with the mortar, okay, like a brick wall, okay, is the masonry. So clay bricks, concrete blocks. And this figure shows the cradle to gate embodied carbon for a 300 mm thick insulated masonry wall, okay, like around 50, comparing to concrete, okay, comparing to the same thickness, total thickness of concrete wall, 110. So we can see that using masonry wall will result in a lower embodied carbon, typically. And there are some alternatives to clay bricks and concrete bricks. For example, using this kind of multicellular clay walling system. So in this kind of blocks, there are some internal cavities. So you see there are some holes. So these internal cavities can reduce the weight and also provide insulation, okay, provide noise and also thermal insulation. And the next one is hem block, okay, like here. Hem blocks is using the fiber from the plant hem, okay, ma. And made from hemp fiber, and they are biodegradable, okay, biodegradable. And hemp can grow very quickly, so it is sustainable, fast growing, and it can also provide very good thermal insulation and acoustic insulation. Okay, compressed earth block and unfired clay bricks, but they can be used only for the dry climate. Okay, for dry climate, no rain, not humid, then we may use these kind of block, but not possible for Hong Kong. And blocks with cement replacement. Okay, replacing the Portland cement, part of the Portland cement with the GGBS, which is the ground granulate blast furnace slag, or the PFA, the pulverized fly ash. Okay, so these are some possible replacement to the clay brick and concrete blocks. Next would be 3 mm windows and curtain walling. Okay, each 3 mm of glass has an embodied carbon of around 6.8 kg of carbon dioxide equivalent per square meter of surface area. And the framing supporting the glazing can account for half of the embodied carbon. Okay, so not just the glazing, we need the window frame. And the window frame actually constitutes half of the embodied carbon of the window. And these are some examples for your reference. A typical curtain wall framing system comprises glazing and the aluminum mullions, okay, and the transom, okay, some structural elements for supporting the curtain wall. And these are usually made of aluminum, okay, and aluminum has high embodied carbon comparing to steel. The structural components of the mullions and the transom can be replaced with steel or timber to reduce the embodied carbon of the facade system. So use steel and timber to replace the aluminum. And the next one is carpet. Floor finishes can have a significant impact on the embodied carbon of an office building, particularly when they are replaced every 7 to 10 years. So on the podium, if you walk past the podium, you can see there are some carpets or some kind of, like carpet placed on the podium, on the floor of the podium. It's because on Saturday is the PolyU Info Day, and those kind of carpet is only one use. Okay, after the Info Day, they would be thrown away. And in the office of my department, we are also using carpet, and you can see how the carpet deteriorate, becomes very just doesn't look good after several years. And it means that we need to replace the carpet in my office and also in this classroom every several years. So 7 to 10 years is already too long for Hong Kong. So maybe we have to replace it every 5 or 6 years. So in the UK, less than 2% of the floor finishes is recycled, and 90% goes to the landfill. So carpets accounts for 71% of this waste, laminate 13%, vinyl 6%, and with remainder distributed between ceramics, rubber, wood, and linoleum. Linoleum is good; it is renewable. Okay, but other vine and then laminate, these very difficult to be recycled. So to reduce the embodied carbon of the carpet, okay, we may use heavy-duty carpet in high wear areas to extend the lifespan, and choose carpet with minimum of 25% recycled content from the post-consumer waste. So we may specify in the project specification that the carpet should have a minimum, like how much, like minimum 25% of the recycled content. And avoid the use of strong carpet adhesive to allow carpet tiles in high wear areas to be replaced. Okay, so for some area where they may be, so maybe tear very badly, then we can replace it grid by grid. It would be easier. And reduce the cut-off waste, the off-cut waste. So typically 20% of the carpet delivered to the site is wasted. So by careful calculation, estimation, good practice can reduce this waste to only 10%. Okay, next is plasterboard. So plasterboard would be the gypsum board, the drywall, and they are manufactured from either mined gypsum or from synthetic gypsum, so artificial gypsum. And the recycled content of the UK plasterboard products is typically around 76%, and plasterboard is around 100% recyclable. So once again, we may specify the plasterboard products with high recycled content. And the plasterboard are typically used for partition, for interior wall, for the false ceiling, and some wall finishing. And lastly is the furniture. So there is no carbon footprint benchmark in the furniture industry. In addition to initial embodied carbon, the lifespan of furniture and the ability to reuse or recycle at the end of the product's life cycle must also be considered. Okay, so how long do we use that furniture? So the longer we use it, the lower would be the life cycle embodied carbon or the carbon footprint of the product. So one example here would be the cardboard bed in the Olympics in 2024. And they are made from recyclable. They are made from recycled paper, and after the game, okay, the bed can be recycled. The material can be recycled. So, a low embodied carbon chair. Okay, let's say you have a chair made from bamboo. Okay, so it will have a low embodied carbon. Okay, because bamboo is a low carbon material. So a low embodied carbon chair that ends up in the landfill after a couple of years does not necessarily result in a low carbon footprint. Okay, so you use the bamboo as a material. Okay, seems to be a good choice, low carbon material. But if you only use it for a few years and then throw it away and replace it with a new one, then the whole carbon footprint of the building could be high because of this. Okay, just like the example that I used earlier for the straw. Okay, so now in the market you can find some aluminum straw, that tube. Okay, instead of using paper tube, a paper straw or plastic straw. Okay, some of you, okay, maybe environmental conscious, will buy the aluminum straw. But if you only use it several times and then just keep it in the cabinet or maybe just throw it away, then it's not environmental friendly. Okay, so we have to prolong their usage time, use it over and over, then yeah, the whole carbon footprint will be lower. So some general recommendations: avoid over design and waste to reduce the amount of material used. Okay, so specifying standard size can reduce the waste. Okay, some standard size such that we can reduce the wastage. And specify low carbon version of materials whenever it is possible with more recycled content. Use locally sourced materials when possible to reduce the transport carbon. And consider durability and flexibility for future uses to give the building a longer lease of life. It is a good practice to ensure the material that can be easily separated. Okay, and to modify and refurbish instead of demolishing. Okay, and design for easy demolition and reuse or recycling of the components at the end of its life. So these are some good practice. Okay, for reducing the operating carbon, maybe we can take a short break. And after the break, I hope that we can finish the reduction of the operating carbon and also have time to talk about the renewable energy. Okay, so let's take a break of 5 minutes. maybe we can pause the video recording. So for the grouping, so if you go to the Blackboard workshop, yeah, you can see the link to the Google Sheet. Okay, so I think it's week 12. By the end of the semester, you need to do a group assignment about the carbon footprint assessment. Okay, so please form groups of around 8 to 10 members. Although in the Google Sheet, I originally make it 8 to 9, okay, but I think 10 is also acceptable. Okay, so if you have a group members, please put your name here, all right? And please do it before the end of week 8, okay? So please try to form groups and input the names of the group members by 26th of October, okay? After this date, if I don't see the names, your names on the Google Sheet, then I will assign you to a random group, all right? So if you have no preference for group members, then just let me assign you to a particular group, okay? So after 26th of October, I will compile the group list, and then after that, I will upload the group list to the Blackboard, okay? And for the assignment content, I will give you more information later, okay? But in the meantime, please try to form groups. Apart from the group work, you also have an individual assignment. So if you go to the Blackboard, you can see the guideline here and also a Turnitin submission link. So let's take a look at the assignment. So this is an individual assignment. So everyone should do its own and do the submission. So according to the Climate Action Plan 2050, Hong Kong aims to achieve carbon neutrality. While buildings are significant contributors to carbon emissions in Hong Kong, the building sector also presents a large potential for carbon reduction. Compared to new construction, retrofitting existing building poses greater challenges in minimizing carbon footprint. Okay, so this assignment is not about new building. It's about reducing carbon emissions in existing building, okay, by some retrofit, okay, some improvement work. So in this individual assignment, you are required to select one or two carbon mitigation strategies and evaluate their feasibility for implementation in an existing building in Hong Kong. And the suggested mitigation strategies are here, but you are welcome to propose some other options. Okay, so like passive ventilation mechanism, passive daylight features, external shading devices, high performance glazing, and others. Okay, so what you need to do, first of all, is to conduct a brief literature review on the selected carbon mitigation strategies. So maybe you select like an on-site composting system. Okay, so you do a literature review and discuss their effectiveness, relevant case studies, some theoretical foundations that support the application in the selected existing building. Okay, so find one existing buildings in Hong Kong and then select one of these strategies. And let's say, okay, we don't care about the cost. Okay, cost is not a problem. Okay, we just consider the effectiveness. Okay, so you will choose one existing building and then select one reduction strategies applied to that building. Okay, so first of all, do some literature review. Okay, find out is like the effectiveness, the principle, and maybe some case study. And next, give me some application plan. Okay, an application plan. So propose the plan outlining how the chosen strategies can be applied to the existing building that you have selected. And if it is applicable, you can also use pictures and diagram to explain how you will implement that kind of mitigation strategy in the existing building. Okay? And next, analyze the benefits and challenges associated with implementing that strategies in the existing building. Okay, some discussion. Good and bad. Okay, some benefits and the challenges of that kind of mitigation strategies. And lastly, some reflection, okay, reflective section. So conclude your assignment with a reflective section that discuss how your personal experience and values have influenced your choice of strategies. Okay, this is the assignment. And for this assignment, it is only a general proposal and you don't need to do any calculation. Okay, no calculations is needed. Okay, just a general proposal. Okay, of course you can refer to some case study by others. Okay, like in the literature review section, you can refer to some case study by others. Okay, like the application of certain kind of system in other, like in a buildings elsewhere. Okay, and it's proved to be quite effective for blah, 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 okay? So you can apply the case study result by others. But for this existing building, okay, for the existing building you have chosen, you don't need to do any calculations, okay? Just some general comments. And maximum 6 pages, okay, not too much. And single line spacing, and including the cover page and pages for listing the reference. And for the reference, please use the APA referencing style. And the assessment criteria, okay, would be these. Okay, you can refer to the assessment rubrics. Okay, so not a complicated assignment. Okay, but yeah, individual. So everyone need to submit the assignment to this Turnitin link. Okay, so let's continue. So before the break, we have discussed different kind of building materials and their potential to reduce the embodied carbon. And apart from the embodied carbon, we also have the operating carbon. Okay, that is the carbon emissions due to the daily operation of the building. And it will be due to all the building services system. Okay, like the air conditioning, the lighting, and then every kind of electrical consuming or energy consuming equipment. So the operating carbon is actually the largest part in the total carbon of the building life cycle. So if you still remember what we have learned in the lecture last week, the operating carbon is around half of the whole carbon footprint. Okay, around half of the whole carbon footprint. And the operating carbon will depend on the ambient weather conditions. So whether it is a tropical region or temperate regions, the efficiency of the building equipment, okay, how efficient is the lighting, okay, how efficient is the water pumps. And the operating schedule, okay, the longer the operation hours, the larger will be the operating carbon. And also the occupancy density, okay, how many occupants inside the building and the occupants' behavior, whether they will switch off the lighting when they leave the office and so on. Reduce operating carbon use through maximizing passive energy use and minimizing active energy use. So we have active and passive energy. So active energy, okay, like energy, okay, so first of all, what is passive energy? So passive energy would be the energy, or when we work with the external environment, then it is utilizing the passive energy, like utilizing daylight or using natural ventilation. Okay, it is working with the environment. Okay, like when it is sunny, okay, when we have a bright daylight outside, then we harvest the daylight such that we can switch off the lighting. So this is a passive energy, okay, utilizing daylight, natural ventilation, okay, work with the external environment. So this is the kind of strategies that rely on the natural environment and also the architectural design. Okay, so for utilizing passive energy, the architectural design and the external environment will matter so much. And for active energy, it would be working against the external environment. Okay, like, so for passive, we have daylight. Then for active, we have the electrical lighting. Okay, so electrical lighting, the air conditioning, so all these are active strategies. So active energy, so for reducing the active energy, maybe using energy saving appliance, energy efficient equipment, okay, LED, okay, lighting control, and then using thermostat to control the air conditioning system. Activated blinds for blocking the solar heat gain, and then fans, efficient heating and cooling system, solar water heating system, heat recovery system, wind turbines, PV panels for harvesting solar energy, and then to drive the electricity, or to generate electricity, okay, or use the wind energy to generate electricity. So these are active energy. Okay, we actively do something to reduce the energy consumption of the equipment. And for passive energy, is about the architectural design, okay, about the external environment. So a building can be designed with the attention to passive solar issue, like how you orient the building, how you site the building such that it can harvest the daylight, okay, it can utilize more daylight. And the glazing size, like window to wall ratio, how tall is the window, and the location, shading strategies, maybe to block the direct sunlight, okay, so as to reduce the solar heat gain. So these are passive strategies. Okay, for the active system, it would be about the building services system. So approaches to improving building energy efficiency. So we have different kind of building energy efficient equipment, okay, like using LED, task ambient lighting, okay, ask the occupants to switch off the lighting, or maybe some automatic lighting control, or maybe variable speed pump, district cooling, chill beam air conditioning, some high volume, low speed fan, regenerative lift. So all these are energy efficient equipment for lowering the active energy. Some other approach will also include the retro commissioning. Okay, retro commissioning is the fine-tuning of building mechanical, electrical, and plumbing systems to optimize the efficiency of those systems without substantial capital investment. So in a building, we have different kind of system, and these system will need some set point, system setting. But over time, okay, after some years, the building system may become less efficient, and maybe due to the system aging, maybe due to the outdated technology or improper settings. So the retro commissioning will help identify these inefficiencies, inefficiencies, and optimize the system performance. Okay, so this is the retro commissioning. And other would be retrofit. Okay, retrofit will means modifying the original system, equipment, and building elements to achieve higher performance or higher energy performance of the building. Okay, a very simple kind of retrofit will be replacing the inefficient lighting system with LED. Okay, the simplest kind of retrofit for energy saving. And for passive system, okay, like passive ventilation, okay, using natural ventilation system. In Hong Kong may not be too possible because it is a densely packed environment, and then we have many busy roads outside. So and the air pollution is serious. Okay, but elsewhere, okay, like in the rural area, it is more possible to utilize natural ventilation. And for natural ventilation, we may have horizontal cross ventilation, okay, which relies on the pressure difference created by wind to drive the airflow. Another one is vertical ventilation. Okay, we have openings on the top of the building and also at the bottom of the building. And it is primarily driven by buoyancy, okay, which is relying on the fact that warm air will rise and exit through the higher opening, and it allows cool air from the exterior to enter the building through lower opening. Okay, so this is vertical ventilation based on the temperature difference between higher level and lower level. But this will work more effectively for taller buildings. Okay, so if like at least several story. Okay, and for cross ventilation, we need openings on two sides of the buildings. Natural lighting mechanism. Okay, so using daylight, passive daylighting features, or high performance glazing. So passive daylighting features, for example, light pipe, light shelf. Okay, so these are not luminaire. These are not electrical lighting, but light pipe. So light pipe is an opening connected to a pipe and then to the exterior of the building. So it can allow sunlight and daylight to enter the pipe and then distribute to the interior. Okay, and we also have light shelf, okay, which are some reflective surface allowing the daylight enter to deeper part of the building. And high performance glazing. So high performance glazing include the low E glass and also spectrally selective glazing. So this kind of glazing will block the unwanted infrared but allow the visible light to enter. Okay, so unlike low E glass, for low E glass, it will block the infrared and also the visible light. Okay, but for the spectrally selective glazing, it will allow more of the visible light to enter, so that we can block the solar heat gain and at the same time utilize the daylight. Okay, estimating operating energy consumption. Okay, actual energy consumption records obtained from utility bill or energy audit exercise, energy simulation methods, so we can measure or estimate the operating energy of the building, and then by using some emission factor, we can predict the operating carbon. Building design affecting operating energy. Okay, whether you use high or low U value of the building fabric, and then the window size, the building services system. So all these will affect the operating energy. Okay, so the skin load, the building envelope design, the interior loading, like the lighting and the cooling load, all these will affect the cooling load and therefore the operating energy. Yeah, in Hong Kong, the air conditioning system will constitute like 30% of the electricity consumption. So cooling load will affect so much the operating carbon. And some recommendation in the building envelope design, okay, like using efficient building envelope design to minimize skin load, well-insulated building envelopes to reduce the heat loss in the winter and reduce the heat gain in the summer, properly designed overhangs to shade can minimize the solar heat gain and reducing cooling load. So in Hong Kong, we have a long cooling season. Okay, long cooling season means we need cooling from the air conditioning system, okay, because we have a long summer, okay, long summer and therefore long cooling season. And a major portion of the cooling load is due to the solar heat gain, okay. So we may use some overhang, okay, some shading to block the direct solar or the direct sunlight, and it can reduce the cooling load. Light color or reflective material can reflect heat can reduce the heat absorption and lowering the cooling energy requirements. So once again, reflect away the radiation, and it can reduce the cooling load. Poorly sealed envelopes allow air leakage, leading to increased energy costs of the HVAC system, and the HVAC system need to work harder to maintain the desired temperature. So this is the infiltration. So if there are leakage in the building envelope, then the hot air may enter the building and once again increasing the cooling load. This is only a diagram explaining the cooling energy and the electric lighting energy for different kind of glazing. So for the clear glass, it can allow light to pass through, and it will allow more solar heat gain, and therefore the cooling energy will be high. Okay, and for reflective glazing, it reflects a lot of daylight, and therefore you need to spend more energy on the artificial lighting. Okay, but for the reflective glazing, it can reduce the solar heat gain, so lower cooling energy consumption, so less consumption for the air conditioning system, but more consumption for the lighting. And in the contrast, for the clear glass, okay, it will result in higher air conditioning consumption, but lower electric lighting consumption because it allows a lot of daylight to enter. Okay, and of course, we have some advanced glazing, okay, thermochromic glazing, photochromic glazing, electrochromic glazing. So the transmittance may change in response to the lighting level, for example. So for photochromic glazing, is that the transmittance of daylight will change, okay, in response to the daylight availability. When there is so much daylight on the facade, then the transmittance will be higher, okay, and therefore blocking the unwanted daylight. Or when the daylight availability is less, then the transmittance could be higher, okay, and allowing more daylight to transmit, and therefore saving the electric lighting. Okay, but at the same time, it will also allow the solar heat gain, and therefore resulting in high air conditioning energy consumption. Okay, and for thermochromic, just the other way around. Okay, instead of blocking daylight, it targets to block the infrared radiation. And infrared radiation would be thermal heat gain. Okay, but blocking the thermal or blocking the infrared may also block the visible light at the same time. Okay, anyway, just a diagram explaining different kind of facade. Okay, lastly is about renewable energy. Okay, some utilizing PV panel or maybe some solar thermal system for reducing the carbon emissions. Okay, on-site renewable energy is seen as a key component to reduce carbon footprint of a building and to achieve the zero carbon goals. So if you remember in the lecture last week, we have discussed about the lowest energy office building, right? So the lowest energy office building, okay, will still have certain carbon emissions. So how to achieve zero carbon building? we need to rely on the renewable energy. Okay, maybe on-site or off-site renewable energy. And can urban commercial buildings become zero carbon by using on-site renewable energy system? So like PolyU, okay, PolyU is located at the city center in Tsim Sha Tsui, and we consume a lot of electricity. So can we install PV panel on all the rooftop so as to achieve a zero carbon PolyU? Is it possible? So this is something we will discuss in the second half of the lecture. Okay, so before we understand renewable energy or the possibility of achieving zero carbon building, let's discuss two kinds of energy that we need in the building or can be generated from renewable resources. So renewable system can generate two forms of energy used in building, and they are heat and electricity. Okay, so heat, like by harvesting solar energy to heat up water for the showering, okay, for domestic heating or domestic water heating. So this is renewable energy, right? The sunlight is renewable energy. And by using the sunlight, we use it to heat up the water. So this is for providing heat energy, right? So heat is a kind of low-grade energy that is usually generated at the point of use, either in the building or in district heating network. Okay, just like that solar thermal heating system. It is installed inside the building. Okay, so sometimes when we walk past the new territories, when you see the village houses, very often you can find that kind of solar collector on the rooftop. Okay, they are used to heat up the water for the toilets, for showering. And this kind of heat energy is low grade. Low grade means it's very difficult to move it around. Okay, so when you move the heat to elsewhere, there would be energy loss, right? And therefore, it is better to generate the heat locally, okay, locally inside the building and then utilize inside the building. And the demand of heat will depend on the season, right? In the winter, we need more heat, and then in the summer, maybe we don't need that much. Another kind of energy that can be generated by renewable system would be electricity. And electricity is a kind of high-grade energy that can be generated anywhere and distributed through the national grid infrastructure. So high-grade electricity is high-grade because it can be transmitted to other location. And if you have surplus electricity, you can fit into the grid system. Okay, just like for the CLP, they have the fit-in tariff, right? You can install some PV panel in the village house, and then the surplus electricity, you can sell it to CLP, right? So electricity is a high-grade energy which can be transmitted elsewhere. And using renewable system to generate heat usually will be based on the heat demand of the building. Okay, so the local heat demand of the building, and it will determine the capacity of the heating system. But for electricity, the capacity of the system will depend on the space available. So if your building has a large rooftop and you want to generate electricity using PV panel, you may install as many as possible, right? Because you can sell the electricity to the utility company. Okay, but for heat energy, it will depend on how much you need. Okay, for my building, I need only this amount of heat. So I only need maybe a small scale of the solar heating plant. Okay, if I generate more, it would be just a waste, because it's difficult to transfer the heat to elsewhere. Okay, so the renewable heating system will be designed according to the building demand. Okay, according to building demand. While for the electricity, will as much as possible because you can sell it elsewhere. Okay, types of renewable heating system. We have solar thermal system, okay, like those you see in the village house for heating the water. And heat pumps, biomass boiler, okay, like by burning some wood chips, some maybe crop waste, and even animal waste. Okay, these are biomass. And combined heat and power. So you burn these biomass and at the same time generate electricity. So generate heat and also electricity. So combine heat and power. And for electricity generation, PV panel, like photovoltaics or wind turbines, or also combine heat and power for generating electricity. And so up to now, we talk about renewable energy, right? Renewable system. But you have to understand that renewable doesn't mean low carbon. Okay? So renewable system use a source of energy that can be replenished, okay, can be refueled, okay, at the same rate that it is used. So it includes the wind energy, sun, solar energy, biomass. So these are generally treated as renewable. And low carbon system produce energy, heat or electricity, with much lower greenhouse gas emissions than conventional fossil fuel system. Okay, for example, the nuclear power plant. Okay, nuclear power plant is a kind of low carbon system. Because when we use the nuclear power, the carbon dioxide emissions is much lower compared to that by burning the fossil fuel. But is nuclear power renewable? No. Okay, so nuclear power plant is low carbon system but not renewable. And at the same time, biomass, okay, burning biomass, which includes some sawdust, okay, some wooden chips, animal waste. So these has high carbon content, okay, but they are biomass, they are renewable, okay, but by burning these wooden chips, it will release carbon dioxide. So for biomass generating plant, or by biomass electricity generating plant, it is renewable, but not necessarily low carbon, okay? So just to explain, renewable doesn't mean low carbon. Okay, the potential energy and carbon saving in a building by utilizing a renewable energy system may vary with different building location and surrounding environment. Okay, for example, you want to utilize PV panel, okay, harvesting the solar energy and then convert it into electricity. So it depends on the solar radiation, right? And the intensity of the solar radiation will depend on the location. So whether it is in Hong Kong or in the northern region or in Singapore, Malaysia, okay, where there are plenty of sunlight. Okay, so availability of sunlight, the building location, and the surrounding environment. So whether the building is located in a city center, okay, where there are so many buildings around you, many obstruction around the PV panel, blocking the sunlight, or the building is located in the rural area, okay, free from obstruction, such that they can have a lot of sunlight. And also if you want to utilize the wind energy, okay, the wind turbines, okay, also depends on the building location. Okay, strong wind, it needs strong wind and consistent wind energy. So if there is not much obstruction, it will be result in a higher efficiency wind turbine system. Okay, building energy profile, and the energy profile will depends on the building type, occupancy density, what is the function of the building, the facade performance, what type of glazing, the operating hour, fresh air quantities, etc. Okay, all these will affect the potential of energy and carbon savings. So because there are so many variables, so for this structure, we will use two different buildings as an example. Okay, so we have building X, like a typical office building, and a hotel Y. Okay, so two buildings, X and Y. X is an office building, and it will utilize electricity mostly. Okay, but it also needs gas for like heating. Okay, maybe space heating, water heating, and for the hotel, it needs more water and space heating. Okay, these two buildings, in order to make a more meaningful comparison, they have the same gross internal floor area. Okay, same internal floor area, 10,000 square meter. And because they have different usage, and therefore the split of electricity and gas are different. So for the office building X, 67% of the energy consumption would be by electricity, and the rest, 33%, would be natural gas. Okay, and the gas would be for supporting heating, maybe space heating, maybe domestic water heating. And for the hotel, same gross floor or internal area, but the split of electricity and gas are different. 31% electricity consumption and 69% gas consumption. Yeah, because here we assume the hotel need a lot of energy for heating. Okay, because of this function. And next, okay, due to the split, okay, the amount of energy consumption per square meter, and for electricity would be 150 kilowatt hour per square meter. Okay, per year. Okay, annual energy consumption per square meter. Okay, for electricity is this value, and for natural gas is this value. And the proportion would be 67 to 33. Okay, same proportion as what we assumed here. And the total would be this value. Okay, and for the hotel Y, we have this proportion, and such that the electricity energy consumption will be 100, and for the gas 225. And we have different energy costs. And here, for the energy cost, it's not written here, but for electricity, the assumption would be, maybe we can use a table to summarize. Okay, we have electricity cost. So this is the tariff for electricity or gas. So this one for electricity, and then for gas. Okay, the tariff for electricity is assumed to be 0.1 pound for every kilowatt hour. Okay, for every kilowatt hour. And that for gas is 0.035. 0.035. Okay, so using these unit rate, if the energy consumption is 150, so 150 multiply this unit rate, then we have the energy cost, right? So just multiply the unit rate. And for the gas, okay, 75 kilowatt hour per square meter, and we multiply the unit rate, then we have the energy cost for the natural gas, right? Very straightforward. It's just that on this slide, I didn't give you the unit rate. Okay, and for the hotel Y, same. Okay, multiply the unit rate multiplied by the unit rate, then we have the energy cost. Okay? And next is the carbon dioxide emissions. And for the CO2, okay, so the emission rate for electricity is 0.6. So this is the same emission rate that we used in the previous lecture, okay, 0.6 kg of carbon dioxide equivalent. Okay, kg, it's difficult to write on the screen. Okay, kg of carbon dioxide equivalent per kilowatt hour. Okay, per kilowatt hour. And then that for gas is 0.2. Okay, the emission rate. All right. And this is only an assumption for a building in UK. Okay, for a building in Hong Kong, the emission rate would be totally different. All right, so it depends on the fuel mixed of the utility company. Okay, so 0.6 and 0.2. So if we have the emission factor, then energy consumption multiply the emission factor, and we have the carbon dioxide emissions, right? So energy consumption, and then multiply the emissions factor of 0.6 for electricity, and then for gas, the emission factor is 0.2. Okay, and we have 15. All right, and for hotel Y, same. So energy consumption and then multiplied by the emission factors. So we have the carbon emissions and another carbon emissions due to the natural gas consumption. So by using these calculations, we can find out the total carbon dioxide emissions. For building X, 105. And for hotel Y, also 105. So these two buildings, although they have different application, okay, office building and then hotel building, but they have the same area and the same carbon dioxide emissions. All right? So these are our case study, okay? And we want to incorporate some renewable energy on these two buildings and try to find out how much carbon dioxide we can reduce. Okay, so let's say some more assumption. So for building X, the annual heating energy requirement is 68 kilowatt hour of heat per square meter. Okay, and for the hotel Y, because of its function, okay, it needs more heating for the water, for the space heating, and the value is larger. Okay, 203 kilowatt hour per square meter. Okay. And if it's not written on this slide, but these are for domestic water heating. Okay, for heating up water. And the rest, they are for space heating, okay, heating up the space, not water. So these total would be like 6.7%. Okay, so based on these two case study for building X, okay, it is provided that 6.7% of the annual heating energy is for domestic hot water. Okay, and that for hotel Y, okay, the total domestic hot water heating would be 33.3%. Okay, 33.3% of the annual heating. So it means for building X, the heating is 68 kilowatt hour per square meter. And if we multiply 6.7%, this would be for the domestic hot water. okay, for the domestic hot water heating. And for hotel Y, okay, 203, and then multiply 33.3%. So once again, it is for the domestic hot water heating. All right? And we assume all the heating in the buildings is provided from natural gas boiler with an efficiency of 90%. Okay, we assume all the boilers will have an efficiency of 90%. Okay, so next, for installing these renewable energy system, we need to pay for certain amount of capital, right? Capital costs. And for analyzing whether it is economical, viable to install that kind of system, we may use the payback period. Okay, the simple payback period is the number of years taken for the energy cost savings to equal the initial capital cost. Okay, very simple calculation. So the simple payback period will be the capital cost. So how much you spend for installing that renewable energy system, and then divide it by the annual saving of the energy cost. So this is the simple payback period. Okay, and a payback period less than 5 years is usually considered to be reasonable for investment in energy cost saving. So if it is too long, then probably not a good choice. Okay, because like for a building, okay, you need investment, and then maybe the lease is only 10 years, and then the payback period is longer than 10 years, and then it doesn't make sense. Okay, next, okay, the payback period does not reflect the value of money over time or the cost per ton of carbon dioxide saved. Okay, so here is only about money, okay, only about cost saving, but it has no implication to carbon dioxide reduction. Okay, and therefore we may use another indicator, okay, which is called the net present cost for carbon reduction. So net present cost uses a discount rate to estimate the value of revenue and cost in the future based on inflation, interest rate, cost of finance, and risk. So the concept of discount rate is like this. Okay, let's say I give you $100 today. Okay, very happy, $100. But how about if I give you $100 1 year later? So which one is more attractive? Of course, getting $100 today, right? So if I promise you to give you some money 1 year later, then it should be more than $100. Maybe for you, okay, $150. Okay, then it will be the same as getting $100 today. Okay, so this is about the discount rate. Okay, because getting $100 today, maybe you can invest it in the stock market, and then 1 year later you can get $150. So getting $100 today is the same to you, okay, as getting $150 1 year later. And the discount rate for every one of you and me may be different. Okay, for me, I don't know how to invest in the stock market. Okay, I just keep the money in the bank, and the interest rate is like the discount rate. Okay, it is the only way I know to earn money from the investment. Okay, so my discount rate may be just the interest rate, okay, which is 0.00%. Okay, very low. But maybe you know how to invest. Okay, maybe in the stock market or maybe the Bitcoin and so on. Then your discount rate could be higher. Okay, so discount rate is to estimate the value of future money. Okay, that will be the same as the money at present. Okay, so this is the net present cost or the discount rate concept. So let's say in this project we assume a discount rate of 5% and a time span of 15 years. So we will install a renewable energy system, and this renewable energy system will help us to reduce the carbon dioxide emissions. Okay, and we want to find out after 15 years, okay, after 15 years, how much can be saved, okay, how much money can be saved, and how much carbon dioxide can be saved, okay. So the cost of carbon, okay, money per ton of carbon dioxide reduction will be calculated by this equation, okay, which is the net present cost over 15 years with a certain discount rate, okay? So this net present value will be the capital investment in day one, and then minus the net present cost of the money saved every year due to the energy consumption reduction. Okay, I will explain more about this very soon. Okay, so this is the money that we need to spend in order to reduce the carbon dioxide emissions. And this money will be the capital cost minus the saving due to the energy consumption reduction. Okay, so by installing like the solar heating, okay, we can spend less money in the natural gas consumption, okay, because I am using sunlight to heat up the water instead of using natural gas. Then I can save some energy costs for natural gas, right? So I invest in the solar thermal collector. So we have a capital cost, and then we minus the reduction in energy costs within 15 years. Okay, in the 15 years time, it would be the upper part of this equation. And the lower part of this equation is the reduction in carbon dioxide emissions over 15 years. So by using this equation, we will be able to calculate how much do you need to spend for reducing every ton of carbon dioxide. Okay? So the first case study would be about the solar thermal collector. So the solar thermal collector converts solar radiation energy into heat energy, okay, for heating up water. And they are most suitable for domestic hot water for its regular demand all year round. Okay, so in winter, we need hot water for taking shower. And maybe in the summer, okay, you may also need hot water for taking shower. But not for my father. Okay, for my father, he will use cold water, no matter it's summer or winter. Okay, but it's an exception. I think for most of us, we will use hot water for winter and probably sometimes in the summer. So the demand for hot water is rather stable. Okay, so the system are typically sized to supply 60% of the demand, with the remainder provided by a boiler or other heat source. So why is that? Why not 100%? So 100% of the demand would be the maximum demand during winter. Okay, during winter, we need more heat energy for heating up the water. Okay, but for the solar thermal system, we won't design it to meet 100% of the heating demand, because if we design it to meet 100% of the demand, then during summer, probably we will oversupply the heat energy. And these heat energy, which are low-grade energy, they are very difficult to be transferred to other location. Then it is a wastage. Okay, so in order to justify or to balance the space required for installation and then the heating demand, usually we will design it to meet 60% of the maximum heating demand. And we assume the efficiency of the boiler is 90%. Okay, the annual heat output depends on the annual solar radiation on the panel of the building. So how much sunlight you get on the panel, and it is based on the location, the orientation, the tilting angle, and any obstruction surrounding the building. The efficiency of the panels in converting solar energy into useful heat, okay, efficiency also affect the output, and any system loss in the pipework and the storage tank. Okay, so these are some variables which will affect the output from the system. So let's say we assume, okay, for London, for the UK, okay, and the panel will have an inclined angle of 60 degree, and the solar radiation will be this value, okay, 1078 kilowatt hour per square meter of the area of the solar panel. And the annual average efficiency is 40%, and the system loss is 3%. Okay, so based on these assumptions, the annual heat output for every square meter of the panel will be the radiation multiplied by the efficiency, and then multiplied by, consider the system loss, and we have this value. Okay, this is just some assumption. So we assume that for every square meter of the solar panel, it will generate 418 kilowatt hour every year. Okay, then based on this assumption, we can do some calculations. So output 418. So for building X and building Y, same system output per square meter. Okay, same per unit of system output. And the demand are different. So how to calculate this 45,000? Earlier, we have some assumptions of the heating demand for the domestic hot water. So for building X, the annual heating, including water and space heating, is this value. And if we multiply 6.7%, is for the space, is for the hot water. And the unit will be kilowatt hour per square meter. So if we multiply by the area, then we have the domestic hot water demand. And similarly for hotel Y, also multiply by the area, then we have the hot water demand. And the area is 10,000 square meter, right? The area is 10,000 square meter. So by using that equation, we will be able to calculate the annual domestic hot water demand. Okay? Building X and building Y, they have different hot water demand, because for the hotel, we may need more heat energy for the water and for the space heating, okay, providing higher service. And next, we will design it to achieve 60% of the demand, right? So we multiply 0.6, okay, because here we assume 60%, okay? So multiply 60%, okay? So these, here B would be this item, okay? Item B, multiply 60%, then we have this value. So 27,000 kilowatt hour is the target heat capacity of the solar thermal collector for building X. And for building Y, same. Okay, demand, and then multiply 60%, and we have this capacity. Okay, and for the solar system output is 418 per square meter. So demand divided by the per square meter output, then we have the area of the panels. Okay, area of the solar collector panel. So C divided by A. So C divided by A. So here 27,000 divided by 418. Then we have 65. So 65 square meter of solar thermal collector will be able to output this amount of heat energy for achieving 60% of the domestic hot water demand for building X. Okay, and similarly for hotel Y, we also have the area. Okay, next, the heat from the gas boiler. Okay, so the solar thermal collector can only provide 60% of the demand, and for the rest, we need the natural gas boiler. Okay, so the heat required from the natural gas boiler will be B minus C, okay, which is 40% of the heating demand. Okay, so this is B minus C, and we have the heat to be provided by the natural gas boiler. And the gas consumption of the boiler. Okay, so this is the heating demand from the boiler, but the boiler is not 100% efficient. It is only 90% efficient. So the demand divided by the efficiency, then we have the consumption. Okay, so the gas consumption would be this 18,000 divided by 90% efficiency. So we have the consumption. Okay, and same for the hotel Y. And gas consumption without solar. So if we didn't install any solar thermal collector, okay, all heating demand provided by the natural gas boiler, then the gas consumption will be the demand divided by the efficiency. Okay, and we have 50,000. So this 50,000 kilowatt hour is the natural gas consumption if there is no renewable energy. Okay, no solar thermal collector, just natural gas boiler. Okay, and therefore the reduction will be this 50,000 minus 20,000. Okay, we want to find out the reduction of the natural gas consumption. So it will be the original, okay, without any renewable, and then minus the renewable. It will be minus the gas consumption when we have the renewable energy. Okay, so this 30,000 would be the reduction in the natural gas consumption if we install the solar thermal collector. Right? Okay, so how much carbon dioxide is being reduced? So it would be the energy and then multiply by the emission factor of natural gas. And for natural gas, the emission factor is assumed to be 0.2 kg of carbon dioxide for every kilowatt hour. Okay, so by installing that solar thermal collector of 65 square meter, we can reduce 6,000 kg of carbon dioxide equivalent every year. All right, and for hotel Y, the area is much larger. Okay, 969 square meter of solar thermal collector, and therefore the reduction is also more significant. Okay, 90,000 kg of carbon dioxide equivalent. And if we calculate the per square meter reduction, and the area is 10,000 square meter. Okay, this the gross internal area of both building equal to 10,000 square meter. So kg of carbon dioxide equivalent divided by the area, then we have the per unit area reduction, 0.6 and 9 kg of carbon dioxide equivalent per square meter. And remember, the emissions, the carbon dioxide emissions for both buildings has been calculated to be 105 kg carbon dioxide equivalent per square meter. So comparing to the original, okay, now we reduce the carbon dioxide emissions by 0.6, which means the percentage is 0.6% for building X, and for hotel Y, the reduction percentage is 8.6% by installing this solar thermal collector. Okay? So in summary, by installing this area of solar thermal collector, we can reduce 0.6% of the carbon dioxide emissions for building X, and for hotel Y, reduce 8.6%, which is not so much, right? So for building X, only 0.6%, very little, okay, not too significant. So for office building X, less than 1%, okay, 0.6% only. And for hotel building Y, the reduction is 8.6%, which is quite okay, quite significant, but the area of the panel is 9,069 square meter, and the rooftop area is only 1,008 square meter, or around 1,000 square meter. And it means it is quite impossible to install this large area of solar collector in hotel Y. Okay, because to reduce the overshadowing problem, the solar panel to roof area ratio for a panel at 60 degrees in London is usually just 27%. If you place them very close to each other, it will block one another. Okay, so like here, if you put it very close to each other, then this part of the panel will block the sunlight from reaching this part of the other panel. Okay, so this overshadowing effect is not desirable. And it means that we need to place these solar panels further away from each other so as to improve the efficiency of the system. Okay, so typically the percentage is only 27%, and on the rooftop you may understand that we need some plant room area. Okay, so maybe only 75% of the rooftop area can be utilized. So we have an area of 1,008 of rooftop, and then 75% can be utilized. And because of the overshadowing problem, 27% of the area could be used for solar collector panel. So it will be around 200 square meter. So it means at most we can only install solar collector panel of 200 square meter large. So this is the maximum area. So let's calculate the value once again. For maximum area of 200 square meter. So if we have 200 square meter of the area, okay, then multiply 418, okay, which is the system output per square meter. Then we have the capacity of the solar collector panel. Okay, the area is 200, and for every square meter we can provide 418 kilowatt hour. Okay, so 200 multiply 418, we have 83,000 something of heat capacity provided by the solar thermal collector. And 40%, yeah, for the heat of the gas boiler, then it will be the annual demand, B, minus the capacity. So B minus C. Okay, so 675,000 and then minus 83,000, and we have this 591,000 something kilowatt hour, which is the required heat provided by the boiler, by the gas boiler. And the gas boiler has an efficiency of 90%, so divided by 90%, and we have the capacity. Okay, this is the consumption of the gas boiler. Okay, and then this is the original, okay, without any renewable energy. So this minus the G minus F. So G minus F, okay, we have the reduction in the gas consumption. Okay, reduction in the gas consumption, and then multiply by the emission factor of 0.2. So we have the reduction in carbon dioxide, and divided by the floor area, internal floor area. Then we have the per unit area carbon dioxide reduction, which is just 1.9. Okay, so 1.9 kg of carbon dioxide per square meter, which is 1.8%. Okay, this is a percentage. 1.8% of the original carbon dioxide emissions, which is now not very significant. Okay, so it means that even if we have utilized the whole rooftop, the whole available rooftop area for installing the solar thermal collector, we can only reduce 1.8% of the carbon dioxide emissions. Okay, next is to calculate the simple payback period. So let's say the capital cost of the solar thermal collector is £500 for every square meter. Okay, and the annual cost of natural gas, okay, the natural gas tariff is 3.5 pence or 0.035 pound for every kilowatt hour. Okay, then we may use these for calculating the simple payback period, okay, which is the capital cost divided by the annual energy cost saving. So the capital cost is this, okay, the unit rate multiplied by the area. Okay, so for building X, the area required is 65 square meter, and multiply 500, so we have 32,000 pound. Okay, this is the capital cost. Okay, so on the upper part it will be this. Okay, for building X, the capital cost, and the annual energy cost saving. So we can save this amount of gas consumption, right? So earlier in this table or in this table, okay, same, 30,000 of reduction in gas consumption. And for the gas consumption, the tariff is 0.035 pound. Okay, so divide by 100 because we want to convert pence into pound. So the saving in energy multiplied by the unit rate of the gas. So we have the money saved by the natural gas consumption reduction, right? So for building X, we can save 30,000 kilowatt hour of gas or save 1,050 pounds a year. So capital cost divided by the annual saving in energy, we have the simple payback period, which is 31 years. And for hotel, why? Just the same. Yeah, because it is dependent on the efficiency and also the capital cost. So for building X and building Y, actually just the same, no difference. So they have the same simple payback period. Okay, and as I have mentioned, this simple payback period take no consideration of the carbon dioxide emissions. It's only about money, okay, only about the return of the investment. So how can we find out the cost of carbon dioxide emissions? Okay, the cost of carbon dioxide reduction can be calculated using the net present cost value. Okay, so here in this example, the discount rate is 5%, and we also have the inflation rate. Okay, inflation, 通脹, right? Yeah, so anyway, just some percentage or just some like interest rate. Okay, they are something like the interest rate. So the inflation rate is something like the interest rate, and yeah, over time price or the cost of something will be getting more and more expensive, okay, after some years. So this is the inflation rate. And the cost of the carbon for every ton of carbon dioxide reduction will equal to, and we are assuming a time span of 15 years. Okay, after 15 years, the net present cost and then divided by the total carbon dioxide reduction would be the cost of every ton of carbon dioxide reduction. So let's use building X as an example. So for building X, we need to install this area, okay, 65 square meter of panel, and this is the capital cost. So in the first year or in the beginning, okay, in the beginning, we have to spend this amount of money so as to install the solar thermal collector. So this is our investment. Some money, some amount we have to pay, okay, but every year we will get this in return. Okay, every year we can save 1,050 pounds. And the net present cost is calculated to be this value. Okay, so it is something like the initial investment, okay, the amount of investment for installing the solar thermal collector minus the annual saving and multiply 15 years. Okay, something like this. Okay, for installing the solar panel, we need to pay certain amount of money, but then every year we have certain amount of saving, right? And if we are considering 15 years of duration, this is the amount of cost, okay, the cost of this system after 15 years, right? It's just that for calculating this cost, we consider the net present value. We consider the discount rate and also the inflation rate. Okay, so this calculation will be explained very soon, okay, on the next slide. So let's say, okay, after the calculation, this net present value is calculated to be 19,000 pounds. And the saving of or the reduction of carbon dioxide in 15 years will be, so here this is not 1, okay, this is I. Item I would be item I is the total reduction in carbon dioxide in 1 year. Okay, so for building X, it would be 6,000. Okay, 6,000 kg of carbon dioxide equivalent. And if we want to convert it into ton of carbon dioxide equivalent, then we just divide it by 1,000. Okay, so 6,000 divided by 1,000 will be 6 tons of carbon dioxide equivalent for every year. And for 15 years, then we multiply 15. Okay, so this item is the reduction of carbon dioxide in 15 years. So the cost, the net cost, I should say, the net cost of installing the solar thermal collector, be careful, okay, and then divide it by the carbon dioxide reduction. And it would be the cost of carbon dioxide reduction within the 15 years time. Okay? So for building X, the cost is 218 pounds for every ton of carbon dioxide reduction. Okay? So the question is how to calculate the net present cost in 15 years. And we use this table to explain how to calculate the net present cost. And here we assume the discount rate is 5% and the inflation is 3%. Yeah, I know it is a little bit complicated, but actually the calculation is very straightforward. So in year 0, okay, so before the operation of the plant, before the operation of the solar thermal collection plant, we need to invest this amount of money, right? This is the payment, this is the investment for the renewable energy. Okay, some money we need to pay so as to install that solar collector. And then in the coming 15 years, we can save this amount of money every year. Okay, this is the annual saving by the reduction of natural gas consumption, right? Okay, so every year we can save this amount of money. Okay? And we have inflation. So this year, okay, in year 1, this amount of saving is 1,050, but because of inflation, the energy cost will be getting more and more expensive. Okay, so that's why next year we expect the saving will be more. Okay, because the energy cost will be getting higher and higher due to inflation. So year 1, you can save 1,050, but next year you can save more because the energy cost is getting higher. So we multiply 1.03, okay, due to the inflation rate. So the inflation rate is 3%. So 1 plus 3% would be 1.03. Okay, so 1,050 multiplied by 1.03, then we have the energy, or we have the saving due to the reduction in the natural gas consumption. And then next year, okay, inflation again. So once again, multiply 1.03, okay, so 1,082 multiply 1.03 and we have 1,114. And you can see that the saving in energy cost is getting higher and higher every year. due to the inflation. Okay, so this is the concept, simple concept of inflation. And how about this one, discount cash flow? So discount cash flow is the concept that I explained earlier. So everyone will have some investment power, okay, by investing in the stock market or the Bitcoin, or maybe put the money in the bank so as to get the interest. So everyone will have their own discount factor. So getting money now will worth more than getting money some years later. Okay, so we have some discount rate. So this is the amount that we spend now. Okay, the investment is to spend now, and then the saving 1 year later. Okay, the saving the saving 1 year later will be less. Okay, because this is the money that we get 1 year later, and it will be less than the money that we get now, right? So we need to multiply by a ratio. Okay, and this ratio is actually very easy. Just 1 minus the discount rate, which is 5%, and then to the power year. This year is n. So in the first year, this present value ratio is 0.95, and it means that if the discount rate is 5%, then getting $100 now, okay, getting $100 now is the same as getting $95. Okay, 100 multiplied 0.95, so $95 1 year later. Okay, this is the meaning of the discount rate. So if the discount rate is 5% using this equation, and n will equal to 1 for 1 year, then it means that getting $100 now is the same as getting $95 1 year later. Okay, so by applying this present value, it means that saving $1,050 now, okay, is the same as saving $998 1 year later. Okay, and then 2 years later, okay, then this power is 2. So 1 minus 5% to the power 2 will be 0.9. And then it means that saving $1,082 now is the same as saving $976 2 years later. Okay, so by multiplying the PV, okay, multiplying the PV here, we can convert the inflated cash flow into the discounted cash flow. So we can convert all these future money into present money. Okay, all these are future money, future saving, and we convert the future saving into today's saving, okay, into today's money. And finally, okay, we can add all these up. So 32,500, and then minus this value, minus, and the total would be the last value, 19,592. And this is the net present cost of installing the solar collection panel in 15 years time. Okay, so we put this into the equation and we can calculate the net cost for reducing every ton of carbon dioxide equivalent. Okay, and for PV panel, we can do similar calculations. Yeah, due to the time, maybe I will quickly go through these calculations. I think you understand these. So the PV panel, the efficiency will vary with the location, the orientation of the panel, the tilting angle, and the shadowing. And we want to estimate how much electricity can be saved by installing the PV panel in building X and hotel Y. And first of all, we have to determine the efficiency. And here we assume the efficiency of the PV panel to be 11%. Okay, 11%. And for the area of the PV panel, so we assume that we can install 300 square meter of PV panel on the roof. Okay, so these add up to 300 square meter. And we may also install the PV panel on the south facade as shading. Okay, so the PV panel can block the direct sunlight and convert the solar energy into electricity. And we assume this area would be total 320 square meter. Okay, so by using this assumption, we can calculate the amount of electricity saved. Okay, so for roof and sunshade, there would be different solar radiation. Okay, for the roof, on the roof, so the sunlight falling on the roof and the sunlight falling on the shading would have different radiation. Okay, so that, let's say for the UK, okay, these are the typical value. And then we have the area assumed. Okay, and for the system capacity, I think we can ignore this, not too important. And the solar energy on a panel. Okay, we have the area and we have the radiation. So the radiation multiply the area, then we have the solar energy. Okay, so this is the amount of solar energy received by the solar panel. But the solar panel has only 11.1% of efficiency. So for this amount of solar energy, only 11% can be converted into electricity. So for this one, multiply 11.1%, then we have the electricity output from the PV panel. Okay, the amount of electricity generated from the PV panel. And next, we multiply the emission factor for electricity, which is assumed to be 0.6. Okay, we assume the emission factor for electricity in the UK to be 0.6 kg of carbon dioxide equivalent per kilowatt hour. Okay, so this is the amount of carbon dioxide reduction in a year. Okay, and if we divide it by 1,000, okay, which is the area, 1,000 square meter of internal area, then we have 2.1 kg of carbon dioxide per square meter of floor area. Okay, and we can calculate the simple payback period, and we can also calculate the net present cost, just like what we have done for the solar thermal collector, and the cost can be calculated, okay, per every ton of carbon dioxide reduction. Okay, yeah, I know that the calculation is a little bit complicated and maybe tedious, okay, very trouble calculation, but this is a way for us to justify which strategy is more cost effective. Okay, like we may have a diagram like this, okay, we may have some statistic, okay, about the cost of carbon reduction for different kind of renewable system. Okay, so earlier we have discussed the solar thermal collector. For every ton of carbon dioxide reduction, okay, you have to spend like more than £200. And for PV panel, okay, maybe it's cheaper. Okay, and then for wind turbine, maybe according to some case study, it's actually very expensive. And then for gas, combined heat and power, okay, actually you can have profit from installing the renewable energy plant. Okay, so these complicated calculations explain how we can come up with this diagram. Okay, after calculating the net present cost and then divided by the carbon emissions in 15 years, then we can find out this unit cost of carbon reduction. And we can compare with different kinds of renewable energy. Okay, so on-site renewables are not the silver bullet to significantly reduce the carbon footprint of the building. Okay, especially for the buildings within the city center. Okay, within the city center, like in Tsim Sha Tsui for PolyU, okay, over the surrounding, we have so many other buildings, and we don't have enough area for installing the PV panel or the solar collector so as to achieve the zero carbon building. Not possible. Okay, not possible to rely on on-site renewables energy. Okay, so reducing energy consumption of buildings is a fundamental. Okay, so better energy efficiency of the building services system would be essential. Okay, reducing your energy consumption. And investment in decarbonization of the electricity grid through large-scale off-site renewables will clearly be necessary to achieve zero carbon building. So if Hong Kong, okay, wants to achieve carbon neutrality, we cannot rely on on-site renewable energy. Okay, installing the PV panel in all the buildings in Hong Kong will not get you to carbon neutrality. Okay, we need off-site renewable system. Okay, in the far-away area, large-scale PV panel or wind turbines may be able to get you to zero carbon. Okay, so for zero carbon buildings, these are the 4 essential strategy to achieve zero carbon building, and they are decarbonization, and then decarbonization will be like renewable energy, and then choosing low carbon material, and electrification is switching from fossil fuel to electricity. So instead of heat energy, maybe we can switch to electricity. Okay, like switching to electric vehicle, switching to electric or induction stove, okay, switching from gas boiler to electric heater. Okay, these are electrification. And then increasing efficiency, digitalization like IoT, and then using different sensor and controller, and to improve the system performance. So these are digitalization. So these are the 4 key strategy to achieve zero carbon building. And I think for the rest of the slides, you can read it yourself. Okay, so I will just stop here. Sorry for the delay. And next week, we will continue the lecture.